Hello everyone, welcome to my class. In today's class, I'm going to cover strategy for testing series. So let me start the class right away. Quick recall, there is no new materials to cover in this section. It just summarizes several tests for series, convergence or divergence that we learned in preceding sections. Sometimes the problem is to decide which test or combination of tests to use on which series. Unfortunately, there are no hard and fast rules about which test to apply to a given series can be given, and most importantly, practice. The following strategies that one may find helpful to recognize the forms of the series. So let's move on. Tests that we learned so far are as below. The zero test, also called the divergent test. If you can see at a glance that limit of an not equal to 0 or does not exist, then use the test to show that the given series diverges. 2. Telescoping series. It is of the form summation an minus n plus 1. Easy to compute its partial sums due to a lot of cancellations, and then take the limit of the partial sums. Geometric series. If the series is of the form summations a is the first term, r is a common ratio, so series a r to the power n minus 1 or series a r to the power n, then it converges if the common ratio is less than 1 and its sum is a over 1 minus r. The series diverges if r is greater than or equals to 1. Alternate geometric series. Summations 1 over p to the power n, where p is greater than 1. Harmonic series. It is of the form series of 1 over n and it diverges. The p series. It is of the form series of 1 over n to the power p and it converges for absolute p greater than 1 and it diverges for absolute p less or equals to 1. Series like a p series or g series. If a series has a form that is similar to a p series, for example, the series of 1 over 5 plus n to the power 5, or a g series such as the series of the form 1 over 5 plus 5 to the power n, then one of the comparison tests should be considered, either comparison test or limit comparison test. The idea is the p series should be chosen keeping only the highest powers of n in the numerator and in the denominator. Note that the comparison tests apply only to series with positive terms. Let's move on. Integral test. If s of n equals to f of n, where f is positive, continuous, decreasing on intervals 1 to infinite, and the improper integrals of fx from 1 to infinite is easily evaluated, then the integral test is an obvious possibility. Another test, alternating series test. If the series is either of the forms, the series of negative 1 to the power n times an, or series of the form negative 1 to the power n minus 1 times an, then AST is an obvious possibility. Absolute convergence test. For a general series, that is the series containing both positive and negative terms in any order, then the ACT is effective. RATFACE, a ratio test. If terms of series involve factorials and or exponentials, then the test is effective. The ratio test should not be used for a p series as it's inconclusive. Root test. If terms of series involves nth power, then root test may be useful. Now with this idea, let's do some example. In the following example questions, we indicate a strategy of which series test should be used, but do not fully work out all the details. Great. So, in following questions, determine whether the series converges or diverges. Answer the questions from A through L. So, part A, given series is summation and runs from 1 to infinite of n over n plus 1. Here, let's use the zero test. Limit n goes to infinite of an is limit n tends to infinite of n over n plus 1. Then you factor out from the denominator and cancel the n and take the limit. It turns out to be 1, which is not equal to 0. So it fails the zero test. That means the series diverges. B, given series is summation n equals to 1 to infinite of 1 over n times n plus 1. Let's use the telescoping series. So define the partial sum. So Sn equals to summation k runs from 1 to n of 1 over k times k plus 1. Using partial fraction technique, we can rewrite this equals to the summation as it is, 1 over k minus 1 over k plus 1. And expand here, put k equals to 1. The first term is 1 over 1 minus 1 over 2. The second term is plus, put k equals to 2, 1 over 2 minus 1 over 3, and so on. The nth term is put k equals to n, 1 over n minus 1 over n plus 1. Then the terms cancel here, so negative 1/2, positive 1/2 cancels, negative 1/3, positive 1/3 cancel here. Dot. Similarly, positive 1 over n cancel to the preceding terms here, negative 1 over n. Then what left? The first terms and the last terms left, which is 1 minus 1 over n plus 1. Then take the limit as n goes to infinity. 1 over n plus 1 goes to 0, so we have 1 left. So that means the sequence of partial sums converges, means the corresponding series converges, and actually the sum of this series is 1. Awesome. Let's move on. Part C. So given series is 1 over 5 to the power n, summation runs from 1 to infinite. This is a geometric series with first terms put n equals to 1, that is 1 over 5, and the common ratio is 1 over 5. Then the sum is first term over 1 minus the common ratio, simplify gives us 1/4. So then given series converges, and actually it converges to the number 1/4. Let's move on. Part D. The series of 1 over n times radical n and runs from 1 to infinite. This can be written as summation n equals to 1 to infinite, 1 over n power, here is a 1 plus 1/2 is 3/2, and this series converges, being a p series with a p equals to 3/2 greater than 1. Part E. Given series is summation and runs from 1 to infinite of 1 over 5 plus 5 to the power n. It's like a G series, so we can bound this 1 over 5 plus 5n by 1 over 5 to the n. We drop this 5 out here, and this is 2, and we know 1 over 5 to the power n is a convergent G series. So by comparison test, the bigger series converges means the smaller series also converges. That means the given series converges by comparison test. Great. Let's move on. So part F. Given series n equals to 1 to infinite of 1 over 5 n plus 1. So let's apply limit comparison test with an is 1 over 5n plus 1 and pick bn equals to 1 over n, and we know the series bn is diverges, being a harmonic series. Then in the limit convergent test, let's see the limit of this ratio. Limit n goes to infinite of an over bn equals to limit n goes to infinite. An is 1 over 5n plus 1 over bn is 1 over n. So we flip it, then n over 5n plus 1. Then the limit of this n over 5n plus 1 when n goes to infinite is 1/5, which is positive. And since the series in denominator is divergent, then by limit convergent test, the series of my numerator also diverges. Great. Part G, given series is summation n equals to 1 to infinite of n times e to the power negative n square. For this example, let's use integral test. So suppose an equals to f of n and put n equals to x, so fx equals to x times e to the power negative x square. Keep in mind, you need to show this function is positive. The positivity is obvious. The exponential function cannot be 0 or negative, and you put x is greater than 1 and decreasing, so this should be decreasing, and continuous. Continuity part also obvious. So here the improper integrals of fx from x equals to 1 to infinite is then easily evaluated by u subs. Put u equals to x square, this x square, then take the derivatives. Du turns out to be 2x dx. Divide both sides by 2. It turns out to be x dx equals to du over half. Then rewrite this given integrals I equals to the integrals 1 to infinite, then e power negative u, x dx is du over 2. Oh, there's a typo. I need to divide by 2 here. And the next step, how to evaluate the improper integrals. We take a limit of the definite integrals, right? So introduce a variable t, then take a definite integrals of e minus u from 1 to t and take the limit t tends to infinite. And don't forget we have here's 1/2. Great, and then it turns out to be 1 over now 2 times e. So it converges. Improper integral converges means the corresponding series converges. Great. So let's move on. Part 8. So the given series is alternating series. Then use alternating series test. Here term of the series are positive. The series is decreasing, and limit n goes to infinite of an goes to 0. So that means by AST the series is convergent. Great. Let's move on. Part I. The given series is summation n runs from 1 to infinite of n factorial over n to the power n. So the terms of the series involves factorials and n power. So let's use ratio test. So here limit n goes to infinite of absolute value of n plus 1th term over nth term equals to limit n goes to infinite. So the an plus 1 is put n equals to n plus 1, so n plus 1 factorial over n plus 1 to the power n plus 1 divide by an is n factorial over nn, then we flip it. Then simplify, so this turns out to be 1 over e, which is less than 1, so converges. Aside, if you flip this term of the series here, then obviously it diverges. Great. Part J. The given series is 1 times 3 times 5 times 7 times ... 2n minus 1 over 2 times 5 times 8 times 11 times ... 3n minus 1. So this is our an. So then let's use the RATFACE. So here limit n goes to infinite of the absolute value of the ratio of an plus 1 over an equals to, so from here to here is a an plus 1 terms, this one. So I put here is 2 n plus 1 Similarly down here 3 times n plus 1 and then minus 1. So this is n plus 1 terms, and this part is a nth term, means an. We need to divide, means we flipped it here. Then it cancel out here, so we can cancel this from here to here, cancels here, this one to this one, so only left 2 times n plus 1 minus 1, which is here, over this terms 3 times n plus 1 minus 1. Then FOIL this one and take a limit n goes to infinite. It turns out to be 2/3, which is less than 1, so it converges. Great. Let's move on. Part K. Given series is n equals to 1 to infinite of n factorial to the power n over n to the power 5 times n. So the terms of the series involves the n power. So let's take a root test. So here limit of the nth root of absolute value of an equals to limit n goes to infinite. So the nth root cancel this n power, so we only have n factorial over n to the power 5. Then the next step, limit n goes to infinite. So then factorial is n times n minus 1 times n minus 2 n minus 3 n minus 4 times n minus 5 factorial. I stopped here. And n to the power 5 means 5 many n. 1n, 2n, 3n, 4n, 5n. And let's take the limit. When n goes to infinite, n over n, you cancel, it's just 1. The second, limit n goes to infinite of n minus 1 over n is 1. Similarly, its limit is 1, its limit is 1, its limit is 1, but this term goes to infinite. So that means our series diverges. Great. Now let's do part L. Given series is summation n runs from 1 to infinite of 5 to the power n over 3 to the power n plus 4 to the power n. Let's use divergence test, or we call the zero test also. So here an equals to 5 to the power n over 3 to the power n plus 5 to the power n. Divide by 4 to the power n. Then take the limit of an. So here's 5 to the power n over 4 to the power n means 5/4 to the power n over, in my denominator, 3 over 4 to the power n plus 1. Then take the limit. So here's the ratio is greater than 1. So when limit n goes to infinite, this one goes to infinite. And the ratio of 3/4 is less than 1. So that means when n goes to infinite, this term goes to 0. So we have infinite over 1. That means infinite. This means it does not exist. So by the zero test, the series divergent. Great. So we finished the section 11.7 today. In our next class, we will start power series. Thank you.